Alright, good morning class. How's everyone doing today? That's good, that's good. Who can recap us what we did what we did last class on Tuesday?
It's a signaling model.
What do we do with the signaling model?
We were looking at the sheepskin effect.
So we looked at sheepskin effects. What are sheepskin effects?
It's basically that the difference between that 1 credit hour going from 119 hours to getting that diploma. So the actual value of having that diploma versus not.
Exactly. So like separate and apart from the human capital that's associated with performance, just like having just the physical performance. So we talked about sheepskin effects. You mentioned that we talked about signaling models. And what are we going to do? What is a signaling model? What do we use signaling for in the last lecture?
Different abilities.
Say that again.
You're trying to signal that you're a high type instead of a low type.
And how did you signal that?
You get more advanced schooling.
Okay. But why is that signal effective in the market?
Because you only do it in theory if you have a lower cost. Because if it's too costly, you're not going to do it.
Right. And so this idea that the signaling is going to allow employers to be able to separate between the high types and the low types, that is called what? We have what kind of an equilibrium? A separating equilibrium, right? So the investment in the signal is what's going to differentiate those high ability versus low ability. And the cost structure has to be such that it's optimal for the high types to signal that they're high types by doing what? Right, by going to college, right? But for the low types, trying to fake being a high type by going to school is actually going to be more costly than just revealing their true type and not going to college. So we set out a set of conditions for which we would have a separating equilibrium. Okay. So what we're gonna, and then after that, what do we talk about?
Does schooling increase productivity?
Okay, does schooling increase productivity? And how do we go about, what was the framework that we used for that?
The wages.
Wages? And we said that wages would be affected by what?
How well you do.
Say it again.
How well you do.
What does that mean?
Through having years of schooling,
Say years of
graduate, non-graduate,
So we said, well, suppose we wanted to investigate this question of does schooling make someone more productive, right? We would need to get some data, and we would need a measure of productivity, which in our case we said was wages, right? So we're thinking that firms are going to pay workers the marginal product of their labor. And then we would also need explanatory variables. So the treatment variable of interest in this setup is going to be what? What was the treatment variable?
Just college or school.
The schooling, exactly, because we wanted to see does schooling make someone more productive. Our measure of productivity is the wage, and then our measure of schooling is years of education. But we also, and Anna, you brought up this important point, you also brought up the fact that there are other things that could affect wages, such as gender, demographics, geography, all of these other things too. So we would have to account for those, and we have to control for these things too. And so this is a really nice segue into today's lecture where we're going to talk about regression techniques. And so this is really taking this data that we've observed, and then we're going to say how can we use this data to come up with an estimate for the marginal rate of return to schooling, which is the gamma parameter that we introduced a while back. Right? So far we've just set it up as this is the effect of a change in 1 year of schooling on your wages, right? So again, it's going to be the percentage change in wages for an additional year of school. But we didn't talk about yet how do we get at this gamma given data. And one of the goals of this course is going to be equipping you with empirical methods to be able to test some of the theories and to measure some of the key policy parameters of interest for those who are studying education. And so what we're going to do today is we're going to talk about how do we take this data, embed it in a regression framework, and then come up with estimates for this parameter gamma. So that's going to be the thrust of the lecture today. Okay, any questions on that? Okay, good. But what I'm going to do is I'm going to try to write more slowly and to pause. So if, for example, I've written down a lot of things that you haven't yet been able to digest it, or you're in between writing and trying to understand, just raise your hand and just say, can you give us a moment so that you can digest what's going on? Because I want to make sure that the lecture is proceeding at an appropriate pace whereby you can learn and understand what's going on, and also can digest. Would that help anyone in this class? Okay, hold it up. Okay, good. All right, good. So why did anybody say anything?
We're too busy riding.
Okay, good. Yes. Well, one of your colleagues came to me. He said, you know, I'm really struggling with keeping up with the notes and understanding it and also writing too. And he said, well, a lot of trepidations. And I said, thank you for telling me this, because I'm sure that other people have that problem. But you guys are you're such troopers that you just like, oh, fine, let's just go for it. And I'm like, oh, okay, we can go even faster. No, I'm joking. Okay. All right. Okay. So this is going to be our simple empirical model of education. So this is our simple empirical model. So in our simple model, we're going to have that the log wages of person I is going to be equal to alpha 0, where you can think of alpha 0 as being the expected earnings for a person with no years of schooling. So log wages is going to be alpha I plus gamma times SI plus epsilon I. Now who remembers what SI is going to be? What's SI? It's not Sports Illustrated. What's SI? Yes, SI is the years of schooling. And who can guess what epsilon I is going to be? That's going to be the error term. What's the error term going to capture?
All the variation and why that's not captured by school.
That's excellent. Someone give this young lady a She's on the ball. Okay. So this is the error term. And so the way to think about this is these are unobserved factors. And that's from the perspective of the researcher. Because of course the person will know these things, right? So this is from the perspective of the researcher. So these are unobserved factors that affect individualized earnings. Right? And so, for example, let's say we see two graduates from Clemson. Both of them have the same level of education, right? But they earn different wages. What this error term is going to do is it's going to capture some of the unobservables that are different between those two people. So as the researcher, if we only see years of schooling and wages, then what is an unobserved factor that could drive differences between the wages of two Clemson grads? So they have the same years of schooling. What might be a factor that could drive differences in wages? GPA, right? So something like ability.
Their major.
Another one?
Their major.
Their major, right? Other ones?
Just look at classes.
Specific classes that they take, yeah. So there are all of these other things that they enter into a person's wages that we might not observe. And then at the end of the lecture, what we're going to do is we're going to talk about how does the relationship between the things that we don't observe, these epsilons, and the things that we do observe, like schooling, for example, how does the relationship between the unobservables and the observables affect our interpretation, or at least the value of this gamma that we are going to estimate, right? So for example, if it's the case, as Tom said, that in the epsilons is going to be some measure of ability, and let's say, for example, that higher ability people go to more schooling, right? Then what's going to happen to this coefficient that we estimate on returns to schooling? Is it going to be overestimated or underestimated? Let me say it again. So let's take Tom's point, which is that ability is unobservable. And let's further state that people with higher ability, on average, earn higher wages because they're higher ability. And then secondly, let's also assume that people with higher ability tend to get more years of schooling. If we were to just think about this gamma as representing the relationship between wages and schooling, but ability was unobserved, would this gamma be too big or too small? It would be too big. Okay, and why would it be too big?
It's also including like your experience, that should be an error term.
Exactly. So like, ability is going to positively influence earnings, and ability is going to be positively correlated with schooling. So if we neglect ability, we're going to be saying that, wow, like schooling is really productive, but what this gamma in schooling is really capturing is going to be the fact that people who have more years of schooling also have more ability. And so they're really earning more money in part because they have higher ability. So the schooling is only capturing a piece of that. And here we're going to misattribute that to schooling itself. Does everybody understand that? Okay. Is the pace so far decent? Okay, good. I see lots of smiles. That's wonderful. Okay, great. Okay. So for now, what we're going to do is we're going to abstract from other factors, excluding S. And the reason that we're going to do this abstraction is because I just want to take you through the mechanics of how do you compute the returns to schooling, right? If we added more factors, if we added, say, experience, etc., like you can go through the same setup that we're going to do here and come up with the results. But I just want to really illustrate for you the technique, okay? So I'll put that here as a comment. So for now, we abstract from including other explanatory variables. In our wage equation. For example, experience, ability, gender, etc. And this is in order to illustrate how we compute gamma returns to school. So what we're going to do now is we're going to take a very simple example where it's going to be obvious what the gamma is going to be, right? And what both gamma and alpha 0 are going to be. And then what I'm going to do is I'm going to tell you that this is the formula that we can use to calculate the alphas and the gammas more generally, right? If we had an example that were not so simple. And then we'll work through the formula with this very simple example and show that the formula works. Then what we will do in the next step is we're going to actually derive where the formula comes from. And so I've deliberately chosen it this way so that the example itself will build intuition. So you can obviously see that what returns to schooling for this case is going to be law, right? And so when we use the formula, we can actually verify that. But on the back end, we're going to be able to show you where the formula is coming from. And so you really get a sense of what's going to be happening. And in particular, what's going to be happening to get these gammas in the regression framework that we're going to be talking about is we're going to be trying to create the gammas that best predict the means, or the gammas that are going to minimize the prediction error. So that's going to be the idea behind that. We'll get into more details about that when we actually go through the exposition of how we compute the gammas. Are there any questions? Okay. Is the pace okay for everyone? Okay. All right. So. So, how do we calculate? Now let's use a simple example where this is going to be, let's use a simple example where we have the following data. On log wages. And here's the schooling. So in this first column, we're going to have the student ID. And we're going to have 3 students. We're going to have student number 1, student number 2, student number 3. In the second column, we're going to have years of schooling. And student number 1 is going to have 1 year of schooling, student number 2 is going to have 2 years of schooling, student number 3 is going to have 3 years of schooling. Okay. Then here, we're going to have log wages. And student number 1 with 1 year of schooling is going to get log wages of student number 1 is going to be 5, log wages of student number 2 is going to be 10, log wages of student number 3 is going to be 15. Okay, so this is just the data. Alright, so this is our data. Okay. Any questions before we move on? Let me just give you guys a moment to write down the data. And so I've deliberately chosen the numbers to be very simple. So there are going to be certain things that are going to be very obvious that just pop off the page when you look at this data. And this is just to be instructive.
What is log wages?
So, for example, what this means is so what that means is that the log of the wage of student 1 is equal to 5. And so that means the wage of student 1 is equal to e to the 5. So this is the natural log of the natural average.
Natural log.
Yeah. So this is the natural log. I see a couple more folks are writing, so I'll just take a moment before I move on to the next thing. So we can illustrate this graphically, right? By saying on the horizontal axis, let's put years of schooling. On the vertical axis, let's put languages. Right? Student 1 is going to have 1 year of schooling. So this is S equals 1, 2, 3. And student 1 is going to earn log wages that are equal to 5. Student 2 is going to earn log wages that are equal to 10. Student 3 is going to earn log wages that are equal to 15. And let me ask you a question. What's special about these points, these 3 points?
They're linear.
Can you say that?
They're linear.
It's linear. They all lie on a perfect straight line, right? Okay. Now, we want to calculate the value of alpha, right? Now, what's the value of alpha? How can we calculate the value of alpha from these data? Of gamma, sorry. What is the relationship between gamma and log wages? It's positive. But we can say more about that. There's a specific relationship between log wages and gamma.
Gamma times your schooling equals log wage.
Well,
Plus the factors.
But we have this thing here too, right? So we only wanted to get at just the gamma. What should we do? What happens if we take the derivative of log wages with respect to schooling? What do we get? We get gamma, right? Can those of you in the back here see down to this point here? You know, here?
Sort of.
Sort of?
No one
Okay,
said
but
so.
I'll go back into here. I'll go back into here. Okay. All right. Okay. So notice that the derivative of log wages with respect to schooling is just equal to gamma, right? And so what this implies is that gamma is the slope of the wage locus. The wage locus is just these sets, the line that connects these sets of points here, right? Does everybody see that? Oh, what is the slope of this line? What's that? The slope of this line is 5. Does everyone see that? An increase, so delta S is equal to 1. Delta log wages is equal to 5. Similarly here, we increase years of schooling by 1. And then we also get an increase by 5. Right? So from the graph, we have that gamma is equal to 5. Does everyone follow that? Does anyone who does not follow this? Who follows it? Raise your hand. Okay. All right. Good. All right. Now let me. Yeah.
The delta log W equals 5, that's the difference in counting from 2 to 3. Or
No.
no, 5.
Exactly.
5.
Yeah. Right. Right. Because essentially we're saying is what's the change in log wages So let me do the following thing, which is going to be show you what the formula is that we're going to use to calculate. Can I erase this here? So So for a general set of wage and schooling data, by general what I mean is that we had everything lying on a straight line, right? It could have been the case that not everything lied on a straight line. So let me do an example. We can have years of schooling for long wages. That looks like this. Right? In this case, the line of basket would be something like this. But we wouldn't simply be able to read this off just from the data points because all of the data points don't line up, right? Does everyone see that? For a general set of wage and schooling data, for example, this data here, it's not obvious what the value gamma is. And so here's a formula for gamma. That minimizes the Gaussian error. Those of you in the back can't see below this, right?
I like a little bit.
Okay, so I won't write something, I'll write it over here. Okay, I'm gonna erase this over here. So the formula for gamma is gonna be, gamma is equal to the covariance of log wages, years of schooling, divided by the variance of years of schooling. Who in here has seen what a covariance is and knows what a covariance is? Raise your hand. Don't be shy. Who has not seen what a covariance is? Okay. So let me explain the idea before I put up what the formulas of variances and covariances are. So let me use an example. Let's say I went to a student at the Clemson football game, right? And I asked them a question. I said, what seat do you have? Like, how close is your seat to the 50-yard line? And then I also asked them, how much did you enjoy the game? And so I have these two data points, right? Now, if I see systematically in the population of everyone's answers that those who had seats that were closer to the 50-yard line also reported higher levels of enjoyment from the game, then the covariance between the quality of your seats and your experience in the game would be positive. And so you can think about the covariance as measuring how do two attributes of the data move together. You can have the opposite. You can say, let's say the cost of your ticket and how much you enjoyed the game, right? And so it could be that, well, everybody is kind of seeing more or less the same game, or if we take everyone that's in the same section of the, let's say we take everyone that's close to the 50-yard line, but some people just purchased their tickets really late, and so they got higher prices, but they didn't necessarily get better seats, right? We ask them, well, what's your reported level of happiness, and also what's the price that you paid? We find a negative relationship between them, that those who paid higher amounts of money enjoyed the game less, that the covariance there would be negative. And so think about the covariance as like a measure of how the two things move together. And so for example, you can think about this covariance between the log of wages and schooling as capturing, in general, do we see that wages are increasing with schooling, or do we see that wages are decreasing with schooling and that there's no relationship? Does that make sense? Okay. So let me write down how you would compute the covariance. Are there any questions on that explanation? Okay. Okay. So like, given observations, so this would be, for example, like log wage 1, schooling for person 1, log wage 2, schooling for person 2, to log wage n, schooling for person n, right? The covariance of the log wages and the years of schooling is going to be, so for a given person, what we're going to do is we're going to compute what's the log wages for that person minus the expected log wages for everyone, right? Multiplied by the years of schooling of that person minus the expected years of schooling for everyone. And we're going to take the expected value of that, or the average of that, right? And so what this term is going to capture is how far is person I's wages from the mean wage. And this part here is going to capture how far I's schooling is from the average level of schooling. Does everybody see this? And have you guys seen an expected value before? The expected value is just the average. So let me be more. I want to read this one. Okay. So let's do for this. So let's compute the covariance between the log wages of person I and schooling. Let's compute the covariance between log wages and schooling in the data, right? And so this covariance here is going to be equal to, now we're taking the average, so how many individuals do we have here? Let me pause a minute just so that you can catch me up. We have 3 individuals, right? Okay. And so we take the average, we're going to have a 1/3 up front. Now what's going to be the covariance term for, so there are a couple of things we need to compute. So we need to compute the expected value of schooling, right? Because the expected value of schooling is going to go into the covariance here. Am I moving too quickly right now?
Yeah.
Okay, let me stop for a second. Ask a question.
How did you know to make it 1/3 and not 3? If you said this is just the average.
So the average is going to be, we're going to add up the components for each of the 3 individuals, and then we divide it by 3. So for example, if we wanted to compute average age of these 3 guys here, I'd say, what's your age? What's your age? What's your age? And I would add up each of their ages and divide by 3.
Yeah, I mean, I don't know, I get how to compute an average, but I don't know how to.
No, ask your question.
I don't understand why it's a third and not, like, where do you get the numerator from, maybe?
Oh, so like multiplying by 3 is the same as dividing by 3. So we could have added everything up and divided by 3, or we can multiply by 3.
Yeah, now I get what you're saying. I thought you already, like, okay, I get it.
Yeah, so let me erase this so that that'll make it a bit clearer. Okay, is everyone up to here? Who's still writing? Still writing? Okay. So what we're going to do now is, so to compute the covariance, what we're going to need to do is we're going to need to compute the expected value of wages. We're going to need to compute the expected value of years of schooling. And then for each person, we're going to compute how far is that person's years of wages different from the mean. And also how far is their year of schooling different from the mean. We're going to take the product of these two, and then we're going to do the average of this. And so in a sense, you can think about this as saying, if, for example, years of schooling is greater than the mean, and also wages is greater than the mean, and on average that tends to be true across all of the people in our sample, then the covariance is going to be positive, right? If what we find on average is that wages tend to be, when wages are lower than the mean, that years of schooling tend to be higher than the mean, then we'll find a negative covariance. And so that's kind of the intuition. Any questions before we go to compute the actual numbers? So to compute the expected value of the years of schooling, how do we do that? Right, so we sum up. So person 1 has how many years of schooling? Person 2 has how many years of schooling? Person 3 has how many years of schooling? 3, right? So this is the total years of schooling. Let's divide 2 by the number of people. When we get 1 plus 2 is 3, 3 plus 3 is 6, 6 divided by 3 is 2, right? So that's the expected value for the years of schooling. Right? Now what we're going to do next is compute the expected value for the log wage. How do we do that? Say that again? With these numbers here. Who can tell me what the expected value for the years of schooling is going to be? Exactly. So we add 5, 10, 15, and we divide by what? By 3. And so 5 and 10 is 15, 15 plus 15 is 30. So we get 30 over 3, which is going to be equal to 10. Right? Right, great. So this is the expected value of all of this. Okay. Now, what we're going to do next is we're going to say, okay, now we can compute this covariance term. So for the first person, are you guys still writing? Okay. So for the first person, what we need to do is we need to get person 1's wages. So what's person 1's wages? And what's the mean wage? The mean wage is 10. So we subtract person 1's wage from that. And then we multiply by the difference between person 1's years of schooling from the average years of schooling. So what's person 1's years of schooling? And what's the average? Good, so minus 2. And then we do the same thing for person 2. So person 2 has, what's person 2's wage? 10. Yep, and what's the mean wages? 10. And what's person 2's years of schooling? 2. And what's the mean? Mean is 2. What about for person 3? What's person 3's wage? 15. Person 3's wage is 15, and the mean wage for the population is what? 10. And what's person 3's years of schooling? 3. And what's the mean? 2. Okay. So these are all of the difference. These are the sum of all of the covariance terms. Does that make sense so far? And what do we divide this by? We divide this by 3. And so this is going to equal 5 minus 10 is going to be what? 5 minus 10 is going to be minus 5. Times 1 minus 2 is going to give us minus 1. Right? Plus 10 minus 10 is just 0. Times 2 minus 0 is just 0. So we just get 0 times 0 for person 2. And for person 3, we get 15 minus 10, which is 15 minus 10 is what? And then we get multiplied by 3 minus 2, which is what? 1. And this all is going to be divided by 3. So we end up with minus 5 times 1, which is 5, plus 0, plus 5 times 1, which is just 5, all divided by 3, which is just 10 divided by 3. So this is what the covariance term is going to be. Who has questions about this? Who understands what we did here? Raise your hand. Who does not understand? Okay. Very good. And one thing is, I'm going to check this. Okay. Okay. So we need to compute the variance of the years of schooling. Okay? And the way that you compute the variance is, the variance is the same as the covariance of something itself. So the variance of years of schooling is the covariance of variance with itself. And so that's just the expected value of the years of schooling minus the expected value of the years of schooling squared. So it's just the squared deviation of the years, expected value of the years of schooling from itself. Right? And so the way to think about this is, what you want to do is, if we have a mean, we want to see how far people are from the mean. The reason why we don't just take an average is, imagine that we had a mean here. You have these 3 people, right? And we have one person whose years of schooling is 2. We have another person whose years of schooling is going to be 1. And the years of schooling for this third person is 3, right? We already said that the mean is going to be 2 from over there, right? And so if we just look at the deviation, if we just look at the expected value as I minus, I'll just say this in words. This person is plus 1 above the mean. This person is minus 1 above the mean. And so if we just added up the deviations here, those deviations would cancel. And so the reason why we take the square deviations is, this person is 1 below the mean, and when we square that, we get 1, and when we square this, we get 1 as well too. Make sense? Okay, so let's compute the variance of S. I should also write that this is the same as the expected value of S squared minus the expected value of S, this quantity squared. Okay. Is everyone following me so far? Is anyone confused? No? Okay, good. All right. So what we need to do to calculate the variance is just calculate the expected value of S squared. But once we do that, we can calculate the variance. We know what the expected value of S is. Right? And so let's compute the expected value of S squared. That's just going to be person 1's years of schooling is 1, so we just do 1 squared. Plus person 2's years of schooling is going to be 2, so we just do 2 squared. Person 3's years of schooling is going to be 3, so we do 3 squared. And we divide that by 1. Great. So we're finding the average value of the years of school squared. That's what we're doing. So you can think about our data as we just have another term where we have years of schooling squared, and it's just 1, 4, and 9. And we're just computing the expected value of this new variable here. So there's no magic or anything crazy going on here. And so this is just going to be 1 plus 4, which is going to be 5. 5 plus 9, which is going to be 14, right? So this is 14. Okay, good. All right. So now the variance is just going to be the expected value of SI squared minus the expected value of SI, this quantity squared. So that's just going to be this first term here, and the expected value of SI squared is what? It's just 14 over 3, right? And the second thing is going to be the expected value of SI, which is 2, this quantity squared. Does everyone see this?
Can you repeat that again? Which one is the expected value for the second one?
This is the expected value for the first one.
Yeah.
This is the expected value for the second one.
Why is it both?
Because it's this quantity squared here. Right? What's your question?
Where are you getting that?
The definition of the variance is the expected value of SI squared minus the expected value of SI is quantity squared. This is the definition.
So where did you get the first one?
So
Subtract the same number of passes.
we know what the expected value of SI is from over here. It's just 2, right? And we know what the expected value of SI squared is. It's 14. So we can subtract these two quantities. When we do the subtraction, we get 14 over 3 minus, this is 4. So to get 4 over 3, we can just say minus 12 over 3, right? So this is just 2/3. Does everyone see that?
I thought the squared, like, for subtracting, I thought you took the expected value minus the expected value squared.
But yeah, this is the same thing as this. So to see that,
So then, why do we have two different numbers? 14 over 3 minus 2, should those be the same?
no, they're not
One
the same.
squared.
No. So this is the expected value of SI squared. So let's imagine that there are two variables. This is the variable SI, and this is the variable SI squared. Right? And we're computing the expected value of this, and then we're squaring the result. And then we're computing just the expected value of this by itself. Does that make sense? You don't understand?
No, I understand, like, I just, like, for my econometrics class, I like, was, I don't know, maybe I was doing it wrong in that class.
No, you're saying that, you're saying this, just compute this here.
Yeah.
Okay, let's compute this here. Let's do that. All right. So for person 1, what's the value for person 1?
1.
It's 1 minus 1. 2 square, right? What's it for person 2? 2 minus 2 squared, right? What's it for person 3? It's going to be 3 minus 2 squared, right? And then we divide this by what? We divide it by 3. Okay, what's this first term here? Okay. What's the second term here? Okay. What's this third term? 1. Okay. And we're dividing by 3. So what's the answer here? 2/3. What did we find for here? 2/3. So these are equivalent. The expected value of SI minus the expected value of SI quantity squared is the same as the difference between the expected value of the variable squared minus the expected value of the variable quantity squared. This is just an identity. Does that make sense? Anybody else have a question on that? Okay, so what I'm going to do is, we're almost home. So we claimed that this is what gamma is equal to, right? So what's the covariance of the log of the radius of SI? We found out already. What's that value? What's that? 10/3. And we want to divide through by the variance of SI. What's the variance of SI? 2/3. So divide that by 2/3, right? That's the same as 10/3 times 3 over 2, which is what? Everyone sees this step here? So your 10/3 divided by 2/3 is the same as 10/3 divided, 10/3 times 3 halves, right? And that just gives us what did we say the slope of that line was?
5.
And so you may be asking, okay, why do we go through all of this rigmarole to do this when we just got to see that was 5? The reason why we did that is because there are going to be certain contexts where all of the points don't line up on a straight line. And so we have to figure out what's the value of gamma that's going to best explain the data. And so I deliberately picked an example where it was obvious what the returns were, so that when I use the formula, we could get the same answer, and you can see, okay, this formula works. What we're going to do is we'll take like a 3-minute break, and when we come back, what we'll do is I'll show you like the nuts and bolts behind how we get this particular formula. All right, so let's take a 3-minute break, observe the breather, and then we'll come back.